So the 2's will change their positions. So now we have 2 and 2. Then we negate 3 and 1. Minus 3 and minus 1. So now we remove the inverse. Then 4 and 2. So now we multiply these two matrices. This means x1, x2 will be equal to a matrix of 2 times 4, which is 8. Then minus 3 times 2 is minus 6. And minus 1 times 4 is minus 4. Then 2 times 2, 4. That is plus 4. So now x1, x2 will be equal to a matrix of 8 minus 6, which gives 2, and minus 4 plus 4, 0. So this implies that x1 is equal to 2 and x2 is equal to 0. Okay, so let's check whether the value of x1 and x2 is correct from the equation given. We know that the first equation given is 2x1 plus 3x2 is equal to 4. 2x1 plus 3x2, 3x2 is equal to 4. And the second equation given is x1 plus 2x2 is equal to 2. So we have found that in our calculations, x1 is equal to 2 and x2 is equal to 0. x1 2, x2 0. So now we are going to substitute these values in these equations. x1 is 2 into 2 plus 3 into 0 as x2, which is equal to 4. 2 times 2, 4, plus 3 times 0, 0, which is equal to 4. Therefore, 4 is equal to 4. This is correct. Then now let's go for equation 2. x1 plus 2x2 is equal to 2. So now let's substitute 2 plus 2 into 0 as x2 is equal to 2. 2 plus 0 is equal to 2. Therefore, 2 is equal to 2. This is correct. So now we have solved this by matrix inverse method. So now let's go and solve it by Gauss-Jordan method. So given the linear equations or the systems of the equation as 2x1 plus 3x2 is equal to 4 and x1 plus 2x2 is equal to 2, then the first thing we have to do here is provide a matrix for the coefficients and the constant values for these equations. 2, 3, 1, 2, and make a line here. Then the constants 4 and 2. Then we close the matrix. So now this is how to do the first step. Then this is row 1 and this is row 2. So now the second step here is now row 1 will change to row 2 because the first least number in the rows that comes is 1. Always make the least first number to be a row 1. So now this matrix will look like 1, 3, 2, then 2, 3. Then the constant 2 will change their positions, 2 and 4. So now this becomes row 1 and this row 2. So the next step here is these 2 and these 2. We are going to make them zeros. And this 1 will remain 1 and this 3 will change to 1. That means we are going to make this matrix an identity matrix. Main diagonals to be 1 and these to be zeros. So let's see how to do it. Row 1 will remain row 1. We are not going to touch the row 1 now. And row 2 will change to -2 row 1 plus row 2. That means we are going to correct row 2 from -2 row 1. Looking these rows and these rows, we are going to change row 2 from row 1. Then we are adding the row 2 again. So this will look like we are going to keep our row 1 since row 1 remains row 1. 1, 2 and 2. So now we are going to look and change row 2. Row 2 is -2 row 1 plus row 2. -2 row 1, -2 times 1, then plus row 2 plus 2. This means we have 0 here. Then now row 2 is -2 row 1. That means -2 times 2, then plus row 2. And the other number in row 2 is 3. Then we have -1. And -2 row 1. That means -2 times 2. Then plus row 2. That is 4. Then we have 0. That is -4 and 4, 0. Then this is row 1. This is row 2. So now we are going to make this 2 to be 0. And this -1 to be 1. So let's move and continue. So now row 1 remains row 1. We are going to change row 2 to be -1 all over 1 row 2. This will make -1 to be 1. Still row 1 remains row 1. So that means 1, 2 and constant 2. So now row 2 will be -1 all over 1 times row 2. That means -1 over 1 times 0, which is 0. Then -1 all over 1 row 2. That means -1 over 1 times -1. This will be 1. And -1 over 1 times row 2. That means -1 over 1 times 0. This is 0. So this is row 1 and this is row 2. So the last is these 2 to be 0. So now row 2 will remain row 2 since it is all corrected. And this is 0, 1. That means it will remain row 2. And row 1, in order to make this 2 to be 0, it will change to -2 row 2, then plus row 1. That means this will be a matrix of row 2 remains row 2, 0, 1 and 0. So then now let's see how row 1 will change. -2 times row 2 plus row 1. That means -2 times row 2 is 0. That means 0. Then plus row 1, that is 1. Then -2 times row 2, -2 times 1. Then plus row 1, that is 2. This is 0. Then -2 times row 2, that is -2 times 0 plus row 1, 2, that is 2. So now this is x1 and 0, 0 and x2. So therefore this implies that x1 is equal to 2 and x2 is equal to 0. So this is correct as the first one that we found. X1 is 2 and x2 is 0. So this is how to solve by Gauss-Jordan matrix method. So now let's move to the next question, question number 4a, and see what it says. Number 4a. Question number 4a says, if a is this much, deduce the formula of a. That means for a determinant, a is given as alpha, again alpha, then beta, sigma, viscosity, and sigma again, then lambda and psi. Lambda or wavelength, all the same. So then we are going to deduce for a determinant. Solutions. First, don't forget to put your sign, positive, negative, and positive. A determinant will be equal to, then we carry the first alpha, then we close its column and it is row, then we go for the remaining ones. That means sigma times psi, sigma times psi, minus viscosity times wavelength, viscosity wavelength. Then we carry the next men, minus beta. Then we close its row and its column. Then we go for the remaining ones. That means alpha times psi, alpha times psi, minus alpha times wavelength, alpha wavelength. Then we carry the next and the last men, that is sigma. Then we close its column and its row. Then we go for the remaining ones. That means alpha times viscosity minus alpha times sigma. Then now a determinant will be equal to alpha times this value will be alpha into sigma psi minus viscosity wavelength, then minus beta into alpha times psi minus alpha wavelength plus sigma into alpha viscosity minus alpha sigma. Then now we open the bracket. A determinant will be alpha sigma psi minus alpha viscosity wavelength minus beta alpha psi, then minus times minus plus beta alpha wavelength plus sigma alpha viscosity minus times plus minus, then sigma alpha and sigma. So now this is the deduced formula for a determinant. So now let's move for the next. It says let a be all these values. All these values are given as numbers. All these variables are given in form of numbers. So let's verify that a determinant is equal to a transpose determinant. So as all these values are given, alpha equal to 1 and all equal to this much. So now we are to verify that a determinant is equal to a transpose determinant. So first we are going to provide the A matrix: alpha, 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 beta, sigma, and viscosity, then sigma, wavelength, and psi as given in the question. So now we are going to substitute all these values. Now A will be a matrix of alpha, alpha, alpha are 1, then beta is 2, sigma is 3, viscosity is 5, sigma 3, wavelength 4, and psi is given as 7. So now this is matrix A. So we are going to find the determinant of this matrix. A determinant will be equal to carry 1, close its column and row, then we go for the remaining values. That means 1 into 3 times 7 minus 5 times 4, then plus minus plus, don't forget. Then we have the next minus 2 into closed its column and row, then the remaining values 1 times 7 minus 1 times 4. Then we go for the last main value, that is plus 3 into close its column and row. Then we have 1 times 5 minus 1 times 3. So now we comes and calculate again. The determinant of A will be 1 into 3 times 7, 21, minus 5 times 4, 20, into minus 2 into 1 times 7, 7, minus 1 times 4, minus 4, then plus 3 into 1 times 5, 5, minus 1 times 3, 3. Then A determinant will be equal to 1 into 20 minus 20, that means 1 into 1, then minus 2 into 7 minus 4, that is 3, then plus 3 into 5 minus 3 is 2. So now this implies that A determinant will be equal to 1 times 1, 1, minus 2 times 3, minus 6, then plus 3 times 2, 6. Therefore, A determinant will be equal to minus 6 plus 6 plus 1. Then this gives 1. A determinant is equal to 1. So now we are going to find A transpose determinant. So now we are finding for A determinant transpose. A transpose first. So now A is given as this matrix: 1, 2, 3, 1, 3, 4, 1, 5, and 7. So we are going to transpose this matrix. A transpose will be equal to 1, that is row to column, 1, 2, and 3. This row to column, 1, 3, 4. And the last row to column, 1, 5, 7. This is A transpose. So we are looking for A transpose determinant. So this will be equal to a matrix of 1, 1, 1, 2, 3, 5, 3, 4, 7. Positive, negative, positive. Always do remember this. So now we are going to find the determinant of this matrix. So here we go. This is 1 first. A transpose determinant will be 1, the first main number in this row. We close the column and row and go for the remaining values. 1 into close column and row and go with the remaining numbers. 3 times 7 minus 4 times 5, then minus 1 into, we close its column and the rows, then this gives 2 times 7, then minus 3 times 5, then the last main number, that is plus 1 into, we close its column and row, that is 2 times 4, then minus 3 times 3. So now A determinant transpose will be equal to 1 into 3 times 7, 21, minus 4 times 5, 20, then minus 1 into 2 times 7, 14, minus 3 times 5, 15, then plus 1 into 2 times 4, 8, minus 3 times 3, 9. So now A transpose determinant will be equal to 1 into 21 minus 20, that is 1, minus 1 into 14 minus 15, minus 1, then plus 1 into 8 minus 9, that is minus 1. So A transpose determinant will be 1 times 1, 1, minus times minus, plus 1 times 1, 1, plus minus minus, 1 times 1, 1. A transpose determinant will be equal to 1 plus 1 is 2 minus 1. That is, A determinant will be equal to 2 minus 1, 1. This is wow. Let's check that A determinant is equal to determinant of A transpose. We find that determinant of A is 1 and A transpose determinant also 1. Wow, that's correct. So now let's move to the next question. The next question says, prove that AB inverse is equal to B inverse A inverse if D and A are invertible matrices with the same size. So first we are to provide two symmetric matrices for A and B. Open a matrix by ourselves, A and B, and this matrix must be symmetric. So let A to be this matrix 1, 2, 2 and 3, and let A matrix B to be equal to a matrix of 4, 5, 5 and 6, a symmetric matrix. So let's see how to solve this question. They said we are going to show that AB all inverse is equal to B inverse A inverse. This is very simple. So first let's find one and go for the other, AB inverse. Now we are going to first find AB. This will be matrix of A times matrix of B, 1, 2, 2, 3, into a matrix of B, 4, 5, 5 and 6. So now we are going to multiply these two matrices. 1 times 4, this will give us 4, plus 2 times 5, 10. Then 1 times 5, 5, plus 2 times 6, 12. Then 2 times 4, 8, plus 3 times 5, 15. Then 2 times 5, we have 10, plus 3 times 6, that is 18. So now matrix AB will be equal to 4 plus 10, 14. 5 plus 12, 17. 8 plus 15, 23. Then 10 plus 18, 28. So this is AB matrix. So we are looking for AB inverse. So now AB inverse, its formula is 1 all over determinant times adjoint of the matrix AB. So now first we are going to find the determinant and adjoint of this matrix. So AB determinant will be equal to 14 times 28, then minus 23 times 17. Then this will be equal to 392 minus 391. So this will be 1. That means determinant of AB is equal to 1. So since we find the determinant, now we are going to find the adjoint of AB. Adjoint of AB. So this will be equal to, we just change and negate as we did before. Change the position of these two numbers and negate these two numbers. That means 28 will be in position of 14 and 14 will be in position of 28. Then minus 23 and minus 17. So this is the adjoint of AB. Now we are looking for AB inverse. Let's deduce the values in the formula. This will be 1 all over, the determinant is 1 as we find. 1 over 1. Then times the adjoint. The adjoint matrix is this. That is a matrix of 28 minus 17. Then minus 23 and 14. So now we are going to multiply this 1 over 1 by the matrix. Now AB inverse will be equal to 1 by 1 times 28 is 28. 1 by 1 times minus 17 is minus 17. 1 by 1 times minus 23 is minus 23. And 1 by 1 times 14 is 14. So the matrix AB inverse is this matrix. So as says in the question, now we are going to find B inverse A inverse to see that whether the values will be the same as AB inverse. So this is the matrix of AB inverse. So now we are to find for B inverse A inverse. First, let's find for B inverse. Will be equal to 1 all over determinant times adjoint of B. So first, let's find the determinant of B. B, as we produced the matrix, is a matrix of 4, 5, 5, and 6. So now the determinant of this matrix will be 4 times 6 minus 5 times 5. That means the determinant of B will be equal to 24 minus 25. Determinant of B will be equal to minus 1. So now we are going to find the adjoint of B. B adjoint will be equal to change and negation of this matrix. 4 will change to position of 6 and we negate 5 and 5. 6 and 4. Then minus 5 minus 5. So this is the adjoint of B. Then this implies that B inverse will be equal to 1 all over minus 1, the determinant of B, times the adjoint 6 minus 5 minus 5 and 4. Now B inverse will be equal to minus 1. 1 over minus 1, that is minus 1 into 6 minus 5 minus 5 and 4. So now we are to multiply this. B inverse will be equal to minus 1 times 6 minus 6. Minus 1 times minus 5 is plus 5. Minus 1 times minus 5 plus 5, and minus 1 times 4 is minus 4. This is B inverse. Now for A inverse. A inverse. This will be equal to 1 all over determinants times adjoint of A. So first we find the determinant, then the adjoint. As we have opened the matrix A, we open it as 1, 2, 2, and 3. So now the determinant of A will be 1 times 3. That is 3 minus 2 times 2, 4. And now determinant of A will be equal to minus 1. So now we are going to find the adjoint of A. Adjoint of A will be equal to, then we change and negate. That is 3 and 1, then minus 2 and minus 2. So this is the adjoint of A. Therefore, A inverse will be equal to 1 all over determinant is minus 1 times the adjoint matrix. This is 3 minus 2 minus 2 and 1. So now A inverse will be equal to this times this, that is minus 3. Minus 1 times minus 2, that is 2. Minus 1 times minus 2, 2. Minus 1 times 1, minus 1. So this is A inverse. So now we are going to multiply B inverse and A inverse. B inverse, A inverse. So this will be the matrix of B inverse. This is the matrix of B inverse. So now we are keeping it down and multiply it with A inverse. That is minus 6, 5, 5, and minus 4. Then multiply by A inverse. Minus 3, 2, 2, and minus 1. So this B inverse, A inverse will be equal to a matrix of minus 6 times minus 3. This will be minus times minus plus, then this will be 18. 18 and plus 5 times 2, that is plus 10. Then minus 6 times 2, minus 12, plus 5 times minus 1, that is minus 5. Then 5 times minus 3 minus 15 plus minus 4 times 2 minus 8. Then 5 times 2, 10 plus minus 4 times minus 1, 4. So now this implies that B inverse A inverse is equal to a matrix of 18 plus 10, that is 28. Then minus 12 plus minus 5, that is minus 17. Minus 15 plus minus 8, minus 23. Then 10 plus 4 is 14. So now let's check whether BA inverse is equal to B inverse A inverse. AB inverse 28, 28, minus 17, minus 17, minus 23, minus 23, 14 and 14. Wow, this is really nice and correct. That is, AB inverse is equal to B inverse A inverse. Correct. The last question says determine those values of t for which 1 is this much and 2 is this much. Let's start with number 1, Roman figure 1. It says t minus 4, 6, 0, t plus 4 is equal to, in matrix 0 is 0, 0, 0, 0 as 2 by 2 as the Roman figure 1 given. So now t minus 4 will be this 0, component by component. And equation 1, this will be this 0, component by component again, as equation 2. So now in equation 1, t will be equal to 4, and t will be equal to minus 4 in equation 2. So this is the answer. Then for Roman figure 2, it says this much, given as 13, 0, 0, 4, t, 0, 3, 2, and t square minus 1 to be zeros. Then this t, the middle one, will be equivalent to the middle 0. That means t is equal to 0. And this, the last t square minus 1 will be the last 0. T square minus 1 will be 0. So now t square will be equal to 1. By squaring both sides, t will be equal to root of 1, which is equal to 1. So therefore t is equal to 0 and t is equal to 1.